Pick up the nearest object. Feel its weight. Feel its solidity. This object is real. It has a shape. It has a location. It exists independently of whether you're observing it. It will still be there tomorrow. This seems like the simplest truth possible. Reality is made of objects. Objects are real. They exist. But here's where it gets interesting. When physicists developed frameworks to describe how reality behaves at the deepest levels, quantum mechanics, relativity, modern field theory, those frameworks suggest something more subtle about what real means. This doesn't mean the object in your hand is fake. It doesn't mean the world is an illusion. It means physics describes reality in ways that challenge some of our everyday assumptions about what exists and how it exists. Today, we're going to explore what modern physics actually suggests about the nature of reality and why those suggestions matter, while being careful to distinguish between what we know, what we model, and what remains genuinely uncertain. Let's start by acknowledging what feels obviously true about reality. The world appears solid. Objects have definite locations. When you walk across a room, you move from one place to another in a continuous path. Time flows from past to future. Cause comes before effect. These aren't just intuitions, they're the foundation of how you navigate existence. This everyday understanding of reality is not wrong. It's useful. It's accurate for the scales and speeds at which you live. You can rely on it. Your brain evolved to model reality this way, and that model lets you survive and thrive. When you catch a ball, you're making predictions about how reality behaves based on this everyday model. And those predictions work. So here's something crucial. Modern physics doesn't deny this everyday reality. It builds on it. It asks deeper questions. But the everyday world you experience is not being overturned by scientific discoveries. The issue is that reality is more complex at scales you can't directly observe, at the size of atoms, at speeds near light speed, in intense gravitational fields. And the frameworks physicists use to describe reality at those scales are genuinely different from everyday experience. So what does physics actually study? What is it trying to describe? Physics is not a description of what reality truly is in some absolute metaphysical sense. Physics is a description of how reality behaves. It's a set of mathematical models that let us make predictions about experiments and observations. Here's the distinction. If I ask, what is an electron? The everyday answer might be, a tiny particle. But that's not quite what physics says. Physics says, electrons behave in ways that can be modeled mathematically. In some situations, they behave like particles. In other situations, they behave like waves. We have equations that predict this behavior with extraordinary precision. The equations work. The predictions match experiments. But what an electron really is, independent of how it behaves, is a question that physics doesn't actually answer. This matters because it means physics is not claiming to describe the ultimate nature of reality. Physics is claiming to describe patterns in how reality behaves. Those patterns can be modeled. Those models can be tested. And within those models, some very interesting things emerge. Let's talk about some of those things. In the early 20th century, Einstein's theory of relativity revealed something unexpected. Time and space are not separate, unchanging backgrounds where events happen. They're woven together into something called spacetime, and that spacetime is dynamic. It curves. It changes. This doesn't mean time and space aren't real. It means they're more fundamental and more intertwined than everyday intuition suggested. Time doesn't flow at the same rate everywhere. It depends on gravity and motion. We've confirmed this. We've measured it. Clocks near Earth run at slightly different rates than clocks far from Earth. Astronauts age slightly slower than people on the ground. GPS satellites have to account for relativistic effects or they become useless. So relativity suggests something about reality. Space and time are not separate, absolute, unchanging things. They're part of the structure of the universe itself. Does this mean space and time are fake? It means they're more deeply woven into reality than our everyday model assumed. Then there's quantum mechanics. And this is where everyday intuition really starts to strain. In quantum mechanics, Particles don't have definite properties until they're measured. An electron doesn't have a definite position. It exists in a superposition of possible positions. Only when you measure it does it collapse into a definite state. This seems absurd. How can something not have a position until you observe it? But here's what's actually happening. Quantum mechanics is a model that works. It makes predictions about what you'll measure. Those predictions are right, with precision that's almost unbelievable. Every piece of modern technology that depends on quantum mechanics, lasers, semiconductors, medical imaging, works because the theory is accurate. What quantum mechanics does not claim is that reality doesn't exist without observation. That's a philosophical interpretation, and physicists disagree about what the math actually means. What quantum mechanics does claim is, the mathematical framework that describes reality at small scales is fundamentally probabilistic. Definite properties only emerge when you interact with a system. Before measurement, you have a probability distribution, not a definite state. Now, I want to be very careful about what these frameworks suggest and what they don't. Modern physics does not suggest that reality is an illusion or that the objective world doesn't exist. The object you're holding is still real. It's still there whether you're looking at it or not. Modern physics does not suggest that the universe is fundamentally mental or that consciousness creates reality. Consciousness is a biological phenomenon. Reality exists independently of it. Modern physics does not claim scientists have figured out the ultimate nature of reality. We have models. Those models work. But there are profound questions about what happens at the moment of the Big Bang, about how quantum mechanics and gravity fit together, about why the laws of physics are the way they are, that remain genuinely open. What modern physics does suggest is this. Reality is structured in ways that are more subtle and less intuitive than everyday experience suggests. The properties we think of as fundamental, like the position of a particle or the rate at which time flows, are not as simple or independent as they seem. And those properties are best described through mathematical models that don't directly map onto everyday language. Here's a key insight. Most of the confusion about modern physics comes from trying to describe quantum or relativistic phenomena using everyday language. When we say an electron is in superposition, we're trying to describe something in English that doesn't really fit English concepts. There's no everyday object that's in multiple places at once. So we use this phrase, but it's not quite right. Similarly, when we say spacetime curves due to gravity, we're using an analogy, imagining spacetime like a rubber sheet. But spacetime isn't actually a rubber sheet. The analogy is useful but limited. This is the nature of scientific models. They're approximations. They're tools. They work within certain domains. They break down outside those domains. And the language we use to describe them is always somewhat metaphorical. A physicist knows this. A physicist talks about models and frameworks, not about absolute truth. But in popular science, we sometimes blur those lines. We say things like, quantum mechanics reveals the true nature of reality, when what we really mean is quantum mechanics provides a mathematical framework that accurately describes certain phenomena. The distinction matters. So what can we actually say about the nature of reality, based on what modern physics suggests? First, reality is not made of tiny objects in the classical sense. At the quantum level, the basic constituents of matter and energy are described by fields, not particles. Electrons, photons, quarks, these aren't little balls. They're excitations in quantum fields. They're described by probability distributions. They have properties that only become definite when you measure them. Second, space and time are not separate, absolute backgrounds. They're woven together into a four-dimensional spacetime that curves in response to mass and energy. The geometry of spacetime determines how objects move. There's no absolute time. Time runs at different rates depending on gravity and motion. Third, the universe is governed by laws that appear to be fundamentally probabilistic at the quantum scale. You can make precise predictions about statistical outcomes, but individual events have inherent uncertainty. This isn't because we don't have complete information. Quantum mechanics suggests the uncertainty is fundamental. Fourth, The universe is not divided into separate categories like matter and energy, waves and particles, subjects and objects. These are ways of describing it, models we use. The underlying reality is more unified than these categories suggest. But, and this is crucial, none of this means reality is unreal or purely mental or an illusion. The universe behaves according to these principles whether or not anyone is observing it. The laws are real. The structure is real. The patterns are real. Let me address something directly. You might have heard that observation creates reality in quantum mechanics, or that reality doesn't exist until it's observed. These are common misinterpretations. What quantum mechanics actually says is, measurement affects the system being measured. When you measure a quantum system, you interact with it. That interaction inevitably changes the system. So the result you get depends on how you measured. This is not the same as saying observation creates reality. It's saying measurement is an interaction, and interactions have effects. A tree falling in a forest with no one around still makes sound waves. The forest is still real. Quantum mechanics doesn't deny any of this. What quantum mechanics does say is, at the quantum level, you can't measure something without interacting with it. And the interaction changes the system. So there's a fundamental limit to what you can know about a system before measurement. This is a constraint on knowledge, not a denial of reality. Now, given all this, what does modern physics suggest about what reality is? I think the most honest answer is, modern physics suggests reality is far more structured and subtle than everyday intuition captures, but physics is not designed to answer metaphysical questions about the ultimate nature of reality. Physics is excellent at describing how reality behaves. Physics is not designed to answer why reality exists, or what it means for something to really exist, or whether consciousness plays a fundamental role. Those are valid questions. But they're philosophical questions, not physics questions. Physics works with observable phenomena and testable predictions. When physics describes reality, it's describing structures and patterns and relationships. It's creating models that predict what you'll observe. Those models are incredibly powerful. They've led to quantum computers, GPS, nuclear energy, medical imaging. They work because they accurately capture something real about how the universe behaves. But they're models. They're not photographs of reality. They're organized descriptions of how reality behaves. Here's what I find most remarkable about modern physics. It shows that reality is more integrated and interconnected than we expected. Space and time aren't separate. They're one thing. Matter and energy aren't separate. They're interconvertible. Waves and particles aren't separate categories. They're two ways of describing the same phenomenon. Observer and observed aren't absolutely separate. Measurement involves interaction. Everything is woven together more deeply than everyday intuition suggested. But this doesn't make reality less real. It makes it more intricate, more layered, more worth paying attention to.